Let's look at how to use our laws of exponents or exponent rules to rewrite exponential form into different bases. So part A is basically just review here. All we have to remember is our basic multiplication rules for exponential form. So all we have to do is say how many 5s are there. There's 2 here, 5 there, 10 there. So we add them all together. 2, 5, and 10 make 17. Nothing too complicated there because you got to add the exponents. Over here it's a little more complicated. There's an x in there, but it's not really a different process. It's just 5 to the 2 plus x plus 10. And then our final answer we would just simplify and call that 5 to the 12 plus x. So we can use x's as exponents as well as bases. So you might see some variables here and there also in the exponent. Our division rule is to say keep the base and subtract the exponents, which gives you 10 to the 10. For this one, same idea, keep the base, subtract the exponents. Just your answer has an x up in that exponent, and that's okay. This part here, we're going to give everybody that fifth power. So 6 to the 4th gets the fifth power, and x to the 2nd gets the fifth power. And this is power to a power, so this becomes 6 to the 20th, because you got to multiply the exponents, and x to the 10th. Over here, same idea. We're going to give everybody that fifth power inside. And then we're going to do that power rule again. We're going to multiply the exponents. It becomes 6 to the 5y, and then x to the 10. And these are being multiplied. So we're just going to use a lot more variables in our exponents here. For this part, all we're trying to get at is that we can do things in different orders. If we're trying to plug in 4 for this, you could do 3 to the 4 plus 1 times 3 to the 4 minus 2, and that equals 3 to the 5th times 3 to the 2nd, which is 3 to the 7th. Or we could say, well, we know they both have the same base, and when you multiply with the same base, we just add the exponents, and you keep the base. We keep the 3, and do n plus 1 plus n minus 1, and that gives you 3 to the 2n, I think I missed something here, minus 2, there it is, minus 1, and then I could say put that 4 in for n later, and that would be 3 to the 2 times 4 minus 1, which is 3 to the 7th. So that's that step right there. So either way we do it is fine. You can either put the n in there at the beginning, or we could do it at the end after simplifying. So I'm going to again simplify these using our rules that we know. Multiplying with the same base, we're going to keep the base and we're going to add the exponents. Same thing here, we're going to keep the 4 and we're going to add the exponents here. Nothing new with our rules, we're just looking at it with variables in the exponents. And then just our basic simplifying by combining like terms that we've done, in previous units. That's just back to our 7th grade expressions right there. This one, same idea. We're going to keep the base here. We're going to add the exponents. So 6 minus n plus 7n plus 5. You can probably do a lot of this in your head without showing all the steps. I just think showing the steps might be more helpful so you don't mess up the integer operations here. So you keep the 3. You got 6n total and then plus 11 or 11 or 6n plus 11 or 11 plus 6n is also fine. Doesn't matter the order whenever you're adding. The next one here is a little bit trickier. How can we jump from here right to there? You'll notice here from there to there, there's no 16. So that means 16's got to go. So we got to think about how can I rewrite 16 using only a base of 4? Well, that would be 4 squared would equal 16. So I'm going to replace the 16 with the 4 squared, and I'm going to keep the 4 to the x there. And then from there, we've got the same base. We've got a base of 4. So we can keep that base of 4 and use our product rule to just simply add those exponents, 2 plus x. And then, of course, like I just said, when we add, any order is fine. 2 plus x is x plus 2. So either way you say it is equivalent. For the next one here, we got 8 to the x. And it's a multiple choice question. You'll see the bases here are 2 or are 4. So we got to think, can I get 2 to a power to get 8? Or can I do 4 to a power to get 8? Well, the powers of 2, 2 to the 1st is 2, 2 to the 2nd is 4, 2 to the 3rd is 8. So there we go, there's 8. If you try to use 4, 4 to the 1st is obviously 4, 4 squared is 16, we're too big. So we can't use 4, so it can't be C or D. So 2 to the 3rd is 8, so I can rewrite 8 to the x as 2 to the 3rd to the x. Because again, 2 to the 3rd is 8. So then 2 to the 3 to the x, I could rewrite using our power rule and call it 2 to the 3x. I can multiply those two exponents, and that's why it's equivalent to choice B, because that's just what we have right there, 2 to the 3x. For this one here, we've got different ways of writing n to the 18th. I want you to think about as that is the answer, and these are the problems we're come up with. So what problems have an answer of n to the 18th? You could do n to the 10th times n to the 8th. You could do n to the 9th times n to the 9th. There's so many combinations. You do n to the 20th times n to the negative 2. If you want to get more fancy there. There's 3 different ways. For power rule here, you could do n to the 3rd to the 6th because you're going to multiply the exponents. You do n squared to the 9th. You could do n to the 18th to the 1, technically. There's lots of different ways you can do that with power rule as well. For part C, this is kind of like fill in the blank. I'm going to skip ahead to the next part here to look at some more complicated examples. Here's part D. So it says a different base. We got to change our bases here. So we got to use our power rule in reverse. So we know that when we have a power rule, power to a power, we multiply the exponents. I see 2 exponents here being multiplied. 3 and x is multiplication. That means 3 to the 3 times x. So what I could say is, well, let's call it 3 to the 3, and then that whole thing to the x. Because if we normally go this way. We normally go from 3 to the 3 to the x and call it that. But now we're undoing it going backwards. And then we can say, well, what's 3 cubed? That's just 27. And then keep the x power on there. So now we got a different base. Same thing for this one. We can call it 4 squared all to the y. And then 4 squared is obviously 16 to the y. Number 3 is a little more complicated here. So this one we got to do the same kind of thing. We got to break apart the adding first, though. When you go backwards, it's opposite of order of operations. So normally you would multiply first and then add. But if we're going opposite, we're undoing, we have to get rid of the adding first. So I'm going to break that apart by calling it 2 to the 4b times 2 to the 1. Because our multiplication rule means to add the exponents. Then I can rewrite 2 to the 4b as 2 to the 4 to the b, and then just keep that 2 to the 1 there. Then I can rewrite 2 to the 4. 2 to the 4th is obviously 16. If you just multiply 2 times itself 4 times to the b. But you still need that times 2 on there. We know that 2 is the same thing as 2 to the 1st. So either way you say it is totally fine. Down below, I'm just going to use our rules again here. These have the same base. They're being multiplied. So we're going to add the exponents. So this gives you 2 to the 4x minus 1. This one is power to a power, so it's 5 to the 3x minus 1 all times 2. We're more used to seeing it look like this with our distributing, so feel free to rewrite that if that's easier for you. That gives you 5 to the 6x minus 2. And then this one is our division rule, which we're going to keep the base and we're going to subtract the exponents. Biggest mistake here is forgetting to use parentheses on the bottom one. You got to subtract that entire thing. We don't need parentheses when we're adding because it's the same thing with or without parentheses. But for subtracting, it is different if you don't use those parentheses. So you got to either think about them or show the steps, or write it down. This would be 3 to the 4n minus 1 because you got to subtract that 2n minus 1 from the 6n. For these here, I'm going to, again, just undo these. So this would be 5 squared to the x would be 25 to the x. This one's a little bit tricky. This one you can think of as 4 to the negative 1x, which is then 4 to the negative 1 to the x. And 4 to the negative 1 is 1 over 4 to the positive 1, or just 1/4 to the x. This one is like number 1, 2 to the 5th all to the x is 32 to the x. And then this last one is 10 to the negative 3 all to the x, which becomes 1 over 10 to the positive 3 to the x. It wants us to go into b to the x form, so just something to a power. So we want to get rid of this 3 power down there, which means multiply it out. That gives you 1,000 in the bottom, and that whole thing goes to the x power. It's a little bit tricky where that comes from, but that's equivalent to that expression there. All right, for part G, it says to use a single base. So I'm going to rewrite these pieces using a single base for both of them. 4 I can't make into 32 because 4 squared is 16, but 4 to the 3rd is 64. So that means I got to change both of these bases. So I know 2 to the 5th is 32, and I know 2 squared is 4, so I can use 2 for both of them. So this becomes 2 to the 5th for 32 times 2 squared to the x. Let me just stop a second and show some colors here. So 2 to the 5th is the 32, and then 2 squared is the 4. And then from there, I'm going to try and simplify as much as I can. So this becomes 2 to the 5th times 2 to the 2x using our power rule. And then we're going to just keep the base and add the exponents, 5 plus 2x. And that would be a single base with a single exponent. Over here, number 2, 3 is a little bit easier to work with here with 3 to the x because you can't break that one down further. 3 is prime. 27 is a power of 3. That's 3 cubed. And then now I've got the same base and we're dividing, so that's 3 to the x minus 3. And then the next one is very similar, 4 to the 2x. And then I can call 16 4 squared. Now that they have the same base here, I can just divide or keep the base, which is the division. The division rule says to keep the base and subtract the exponents. So there we have it for that one. Just do a couple more examples here. Which one's not equivalent to n to the 20th? Well, let's go through each one here. Oh, these should be n's. A little typo there. We'll fix that later. This one should be n to the 12th. This one would be n to the 20th. This one would be n to the 20th, power rule. This one's n to the 20th. So it should be the first one if you just ignore that typo where the x's were. That one's not equivalent because it's 12. Why are these two equivalent? Well, let's break this one down. 3 to the 2x plus 4 is equal to 3 to the 2x times 3 to the 4th, which is, let's break this down a little bit further. I'm trying to think if it's easier to break this one. You know what? I might actually go to the other one and see if we can go backwards here. I'm taking a break with the left side here. I can rewrite 9 as 3 squared to the x plus 2. I think it's actually easier to do this, because then I can say, well, 3 squared to the x plus 2, that's 3 to the 2 times x plus 2. And that would be 3 to the 2x plus 4. So I think going that direction is actually probably a little bit faster, a little bit easier to see. You could do it over here too. It would just probably, you just say 3 to the 2 to the x. The tricky part is this part right here, the 3 to the 4th, because you'd have to say 3 to the 2nd squared to see the 9. And that would be 9 to the x times 9 squared, which is why it's 9 to the x plus 2. So you can go either way. I just think going on the right way is probably easier. This last one, 36 times 6 to the 3x plus 1, that's going to be equal to 216 raised to some exponent. That's a little complicated. How are we going to get that? Let's go step by step. So 36 times 6 to the 3x times 6 to the 1, break apart that adding rule there, which happens when you multiply with the same base. And then I'm going to rewrite the 6 to the 3x as 6 to the 3 to the x. I'm going to write that 6 as just 6 and this 36 out front. 6 to the 3rd is 216 to the x, and so is 6 times 36. So I'm going to multiply those two and just call it 216 out front, because you can change the order of multiplication. That's our commutative property. So then this equals 216 to the 1st times 216 to the x, which then becomes 216 to the x plus 1, or 1 plus x. So there we have it as a power of 216. So those are really complicated, but that's how you can change the base using our exponent rules in reverse to find patterns using what we know about powers of different bases.